Okay, so here I want to talk about voltage sources. Voltage sources are obviously something that you must have in a circuit. If you want to have the circuit do anything, you need to have a voltage source or another source like a current source. But I'm going to be talking about voltage sources here, and then in another video I'll cover current sources. And so first I want to show you the symbols that are used in schematics for a voltage source. This is there are two main DC symbols that are used for direct current or DC constant voltage kinds of voltage sources. One is like a battery, and that is obviously a DC source. The batteries, like you go to Rite Aid and buy a battery, that's what you've got. Now note that I've got these open circles here. Those are terminals that would be on the battery, and that's how you buy a battery, right? When you buy a battery, you see a plus end and a minus end. They're not connected to anything, so that's what this is showing here. Same way now with this symbol, this is what you'll find in a lot of textbooks. There's a circle with a plus sign indicating the plus end. Clearly on this one, the long end is the plus end on the battery symbol if you use it that way, if you use that symbol. For alternating current, such as what you get when you plug into the wall, alternating current usually is a symbol that looks like this with a little squiggle inside that's supposed to approximate a sine wave. So that's what you're going to see. And again, voltage sources do not have to be connected to anything and for them to operate as voltage sources. So what you'll see a lot, I refer to fairly often, is what we call an IV curve. So current versus voltage, and what would be the current versus voltage drawing or plot for an ideal battery or an ideal voltage source. The voltage source is basically, in an ideal world, gives you a particular voltage. Say, let's say that this is this point is 5 volts. 5 volts right here, and regardless of the amount of current that is being demanded of this battery, which is what happens when you connect the battery to something called a load, which is a demand for current, then in the ideal battery or the ideal voltage source, the voltage will not change regardless of the amount of current that is being demanded of it in either direction. In other words, you can have current leaving the plus end, or you can have current leaving the minus end. And in the case of it leaving the minus end, that means it's coming in the plus end, and that means, what does that mean? That means the battery is being charged, right? Charged up, like in your car when you charge your battery up. If it leaves the plus end, that means that the battery is supplying energy to a circuit. So either way, doesn't matter, 5 volts, regardless of the amount of current. In the ideal, this could go up to either plus infinity or minus infinity. Obviously, that doesn't make any sense, but theoretically, in the ideal world, that's what could happen. So this is the IV curve for an ideal battery. Well, of course, we don't have ideal batteries, do we? We have batteries that are other than ideal, and they can be represented by a circuit that looks something like this. So I'm just going to draw it as a battery. So we've got some, and let's just say, for instance, it's 5 volts, and we've got possibly, and this is kind of not very good, but we'll just say for the sake of argument here, that we have a 10 ohm resistance that is part of the battery itself. It's inside the battery, and so I'm going to draw a dashed line to indicate that this is all part of the battery itself. So that's a 10 ohm resistance that is inside the battery. It could be the chemical process that's going on inside. That's how batteries make that's how they make their voltages, through a chemical process, and the chemical process is going to, that reaction will occur at the speed of the chemical reaction. You know, we have no control over that. And let's just say that it can be represented by a 10 ohm resistor. Well, clearly, when we have nothing connected to this non-ideal battery, we're still going to read 5 volts at this point, right? Because we have no current going through the 10 ohm resistor. And by Ohm's law, we know that if there's no current through a resistor, IR then must equal 0. And so there's no voltage drop across this 10 ohm resistor. And so all 5 volts appears at this point right here, according to KVL, right? As you add up voltages going around a closed list of voltages, where it ends up where you started from, so you must have 5 volts at this point as well. But what happens when you add a load to this in the form of, say, of a resistor? If you start off with, for instance, a 1K resistive load that I'm just going to show as being attached to the terminals, now what have we got? Well, now clearly we have some current running through this circuit. And what would be the amount of the current? Well, the amount of the current is essentially, it would be some I equals 5 volts over 1,010 ohms, which is approximately 5 milliamps, 0.005 amps, right? So now the question is, how much voltage now because we do have 5 milliamps approximately, just a little under 5 milliamps, going through this 10 ohm resistor. What's the voltage drop across that 10 ohm resistor? Well, the voltage across that 10 ohm resistor by Ohm's law would be 5 milliamps times 10 ohms. And so the voltage across the 10 ohm resistor is approximately 0.05 volts. Not much compared to the initial value. So this load resistor now sees not 5 volts anymore. It sees 4.95 volts. And so if we were to, if we were to plot a non-ideal voltage source on this IV curve, what would that look like? Well, as the current is kind of small, but we would have a point that would be here someplace, plus or minus, and so we would see a slight drop in voltage with a slight amount of current. And so supposing now, instead of a 1K resistor here, we really demand a lot of current from this voltage source in the form of a 10 ohm resistor instead of a 1,000 ohm resistor. Well, in that case, so I'm going to say I sub 1K is this thing, and I'm going to say, now supposing instead of 1K, it is just 10 ohms, 10 ohms. So now the I for 10 ohms will be 5 volts over the sum of these two resistors, which is 20, which is what? Well, 5 over 20 is 0.25, right? So now we're having 0.25 amps. So now we're getting some significant voltage here across this 10 ohm resistor. So now what is the V10? V10 will now equal 2.5 2.5 volts, because it's 10 times 0.25, 2.5 volts. That means that half of the voltage is being dropped across the internal resistance of the voltage source that we have no control over. And so this 10 ohm resistor now is seeing only half of the voltage that the internal that the battery is capable of putting out if there's no load. And so now the curve for a real battery, a real voltage source, looks more like this dotted line than it does the vertical straight line. So in our class, in our world, basically we're going to be dealing with ideal battery sources or voltage sources. And if we want to represent a non-ideal voltage source, then we will put a resistor in series with the battery. And so that is basically this is the end of the voltage source video, and thank you for watching.